We dealt with stoichiometry a few sessions ago, and we are going to deal with it again now. The difference between now and the previous times is that in the previous instances of stoichiometry, we were looking at a chemical process that started out with pure substances as reactants. And we were able to convert between moles and particles, moles and mass, moles and moles, moles of one substance to moles of another substance, using appropriate conversion factors with for this reaction, the chemical process. But more often than not, when we do chemical processes, when we do reactions, we don't start with pure substances. Oftentimes, instead, we use solutions of reactants that are then mixed together, which then undergo a chemical process. The whole idea of stoichiometry is still the same. In other words, how do we go from moles to particles, or moles to mass, or moles of one substance to moles of another substance, using molar ratios from coefficients. I mean, all of those equations still work. Those are absolutely useful. The how do we get to the moles, on the other hand, might be a little different, because now we are not dealing with pure substances, instead with solutions. So for example, if you look at this question right here, it is a reaction that's taking place between silver nitrate and magnesium chloride. Silver nitrate, a solution of silver nitrate whose volume and concentration are given, is mixed with another solution of magnesium chloride to undergo a chemical process. Now, first thing that I want to emphasize on, when we were talking about dilution, we said it is a physical process because the solutes of those solutions were the same in the two solutions mixed together. Here, on the other hand, please note, it is not a physical process. It's a chemical process, because the solute in the first solution is not the same as the solute in the second solution. When silver nitrate solution mixes with magnesium chloride solution, there will be a chemical reaction, a chemical interaction between the two substances. So this is not a dilution problem. In other words, if it's not a dilution problem, M1V1 equals M2V2 does not work here. That is only specifically for dilution cases where which is a physical process. Okay, having emphasized on that, let's look at this one. Since it's a chemical process, it's a stoichiometry problem. In any stoichiometry problem, we must start with a balanced reaction equation. So at this time, I would ask you to pause the recording while you write a balanced reaction equation. Okay, so hopefully you got the balanced reaction equation as 2 silver nitrates react with 1 magnesium chloride to produce 2 silver chlorides and 1 magnesium nitrates. Okay, once this is balanced, what do we do next? See, they're asking us to calculate the mass of silver chloride that can be made. What does that mean? That can be made. Exactly. What they're asking is theoretical yield of silver chloride. Now there are two reactants. The volume of the first reactant is 50.0 mLs. The concentration is given as 0.850 molar. Second one, volume is 85.0 mLs of concentration, 0.720 molar. So, and we need to calculate the grams of silver chloride that can be made. So, how do we do that? What's the next step? Yes, the next step is for us to figure out the limiting reactant. Which reactant will control the maximum amount of silver chloride that can be made in this process? Which means basically, if you remember the process of determining limiting reactant, we select a product to work with. In this case, let's select silver chloride to work with because that's our focus. In other words, in order to figure out limiting reactant, we need to figure out the number of moles of silver chloride we can get from moles of silver nitrate And we also need to figure out the number of moles of silver chloride we can get from the moles of magnesium chloride. And then whichever reactant is capable of producing less amount of the product will be the limiting reactant. Okay, good. Now, um, the question now is, how do we get the moles of how do we get the moles of magnesium chloride calculated, and how do we calculate the number of moles of silver nitrate? Now, please, let's go back to what we already know. We know that molarity equals moles of solute divided by volume of solution in liters. If that's the case, can this equation be rearranged to calculate for moles of solute? Yes, it can. Moles of solute will be equal to molarity times volume. Now, for moles of silver nitrate, do we know volume of silver nitrate solution used? Yes, we do. Of course, it's in mLs. We'll need to convert it into liters. And do we know its molarity? Yes, we do. And so is the case for magnesium chloride. In other words, if you look at the concentration of silver nitrate, it is 0.850 moles of silver nitrate for 1 liter of solution. If this is multiplied by the volume in liters, 0.0500 liters, liters cross out, leaving us with moles of silver nitrate. Moles of silver nitrate can then be crossed out, leaving us with moles of silver chloride from silver nitrate. In the same way, magnesium chloride concentration is 0.720 molar, which means moles of magnesium chloride for every 1 liter of solution, which when multiplied by its volume in liters, liters cross out, give us moles of magnesium chloride. Moles of magnesium chloride cross out to give us moles of silver chloride from magnesium chloride. What about the molar ratios in the corresponding conversion factors? The molar ratios between silver chloride and silver nitrate is 2:2, and that between silver chloride and magnesium chloride is 2:1. When you calculate these number of moles, we get 0.0425 without rounding. Please don't round yet, because these are not our final answers, and 1,224 moles from magnesium chloride. Given this, which reactant is the limiting reactant? Exactly, the limiting reactant is the one that makes less number of moles, and that would be the silver nitrate. In other words, the amount of silver chloride that can be made will be controlled by silver nitrate. In other words, the highest number of moles of silver chloride that can be made is 0.0425 moles of silver chloride, and this can be converted into grams using molar mass of silver chloride, which is 143.32 moles cross out, and this gives us 6.0911 grams of silver chloride. That rounded to 3 significant figures give us 6.09 grams of silver chloride, and this is the maximum amount of silver chloride that can be made given the solutions we are using. The next problem is similar to the one we just did. I would ask you once again to pause the recording while you read the problem, strategize how to solve for it, and set it up. Okay, once again I would like to point your attention to, and this is extremely important for us to remember and understand, that this is not a dilution problem. Since it's not a dilution problem, M1 V1 equals M2 V2 does not work here. This is a chemical reaction where potassium hydroxide solution is reacting with phosphoric acid solution to create new substances, sodium phosphate and water. This is not a physical process but a chemical process. When you balance this equation, you get 3 and 3. We also know in this case that we are using 27.30 mLs of potassium hydroxide solution, and in order to react with that we need 40.00 mLs of phosphoric acid solution whose concentration is 0.833 molar. We need to calculate the concentration of the potassium hydroxide solution. So once again, let's first create a strategy. Knowing the volume and concentration of phosphoric acid, can we calculate the moles of phosphoric acid? Yes, we can. We've done it. From here, using the balanced equation, can we then calculate the moles of KOH that it would take to react with the moles of phosphoric acid? Yes, and that's the whole idea of stoichiometry, is the molar ratio part. And if we know the moles of potassium hydroxide and we know the volume of potassium hydroxide, can we calculate the molarity of potassium hydroxide? Exactly, we can. Okay, so let's set up this problem. So the phosphoric acid molarity is given as 0.833 moles of phosphoric acid for every 1 liter of solution. If this is multiplied by the volume of the solution in liters, that would be 0.04. Please keep track of significant figures. That crosses out liters, leaves moles of phosphoric acid. So now moles of phosphoric acid can be converted into moles of KOH that phosphoric acid will react with according to the equation given, and that ratio is 3:1. Molarity, remember, is moles per liter. In other words, if you were to divide the moles of KOH with the volume of KOH in liters, 0.0273, oops, I'm sorry, there was a zero there, 370 liters. Please notice, at this point, the units are moles of KOH per liter of KOH. Moles per liter is nothing but molarity. Exactly. So when we are set it up correctly, now when you calculate this, we get 3.661538,462 moles of KOH per liter of KOH. That is nothing but molar. And this needs to be rounded to 3 significant figures because of the molarity of phosphoric acid given, and this becomes 3.66 molar concentration of KOH. Okay, go ahead and pause the recording again and while you read the problem and try to set it up. Now this is the finale of the whole course, so to speak. We are combining solutions with stoichiometry in the big way. Once again, the first step, please remember, in all of the cases, especially when we are trying to calculate percent yield, the first step is a balanced reaction equation. The second step is to figure out the limiting reactant. The third step is to figure out theoretical yield. Finally, the fourth step is percent yield. Okay, let's go through these steps in a very systematic way. Feel free to pause the recording every time you need to work on something so that you can take it at your pace. Balanced reaction equation, we are reacting calcium bromide, CaBr2 solution with silver nitrate solution to create silver bromide, and that's a solid, and calcium nitrate. When you balance this equation, you have we get 2 silver nitrates, 2 silver bromides. Okay. Once the equation is done, we go on to our next step. Now, before we do, let's first compile the information given to us. We know we are using 75.00 mLs of calcium bromide, concentration 0.850 molar. We're also using 100 mLs of 0.755 molar silver nitrate solution. The actual yield of silver bromide obtained is 5.500 grams is the actual yield. Okay, so the next step, of course, is to figure out the limiting reactant. In other words, we need to figure out the number of moles of the product, silver bromide in this case, from each of the reactants separately. As we did before, using volume and concentration, we can figure out moles of each of the reactants. So 0.850 moles of calcium bromide for every 1 liter multiplied by the volume in liters gives us moles of calcium bromide. This, using coefficients in the balanced reaction equation, lets us calculate the number of moles of silver bromide from calcium bromide, which calculates out to be 0.1275 without rounding silver bromide. Similarly, 0.755 moles of silver nitrate for every 1 liter is the concentration, multiplied by 0.1000 liters of that solution gives us moles of silver nitrate, which can then be converted into moles of silver bromide using the coefficients in the balanced reaction equation. That, upon calculation without rounding, gives us 0.0755 moles of silver bromide. If that's the case, the limiting reactant is silver nitrate because it leads to less amount of the product. So, if that's the case, the theoretical yield of silver bromide will be the number of moles from the limiting reactant converted into grams by using the molar mass of silver bromide, which is 187.77 grams. That, upon calculation, gives us 14.176635 grams of 6635 grams of silver bromide without rounding. That's the theoretical yield. Therefore, percent yield equals actual yield given 5.500 grams divided by theoretical yield 14.176635 grams times 100 leads us to 38.79623056%. Now this needs to be rounded to 3 significant figures, which gives us 38.8% yield.